This is the first video about valence shell electron pair repulsion theory, thankfully shortened to VSEPR. And I'm just going to do a little bit of an introduction here, give you a bit of an idea about the Canadian content that surrounds this particular theory. I'll give you some definitions, so that's a good pause video moment once you've got through all the definitions. And then I'm going to talk about this very important notion of electron domains and how those electron domains establish differing strengths of forces of repulsion, and it's really how those repulsions establish different molecular geometries. So we might as well get started. So first of all, VSEPR is, as it says in this quote, a super simple technique for predicting the shape or geometry of atomic centers. And so that can be in small molecules or ions. So I like this quote because it says it's super simple. If it's in quotations, it's got to be easy, right? Well, it is actually quite simple. You do have to know some of the background, but once you know this background and understand what it is saying, it is very easy to look at a molecule as long as you know all the electron domains and predict the shape of that molecule. And the second thing I think is useful in this quote is it talks about the shape or geometry of atomic centers. We are looking at the shape around an atom. It can be a central atom in a simple molecule, so something like CH4, methane. The central atom is carbon for that molecule, but it could also be a carbon in a hydrocarbon that we talked about in organic chemistry. So it could be carbon 3 in pentanthreone, for example, so the carbon that contains the carbonyl group in that molecule. So when we say atomic centers, we're often referring to a central atom, but we are not always referring to a central atom. So in terms of the Canadian content, I did just want to mention this gentleman, Dr. Ronald Gillespie, is certainly the preeminent name when people think of VSEPR. Dr. Gillespie was working out of McMaster University when he proposed this model. Now, he wasn't working in isolation. He did have the assistance of an Australian scientist by the name of Ronald Nieholm, and so I guess credit where credit is due. So two scientists, both of whom were are considered to be the founders of VSEPR. But Dr. Gillespie, as I said, he's the one who his name is really associated with this particular theory. So a few definitions. So again, you might want to pause the video when I've finished these and get these down in your notes. So electron domain, as I said, this is pretty important. So it refers to pairs of electrons around a particular atom. And so those pairs could be a bond pair or they could be a lone pair. And as I said, it could be a central atom or it could be an atom in a chain or whatever. But really the geometry is around a particular atom and atoms bonded to it. That's what we're looking for. So those are the electron domains we're considering. Unshared electrons. So we all know what unshared electrons are. These are known as lone pairs. And again, in VSEPR, we're now really only interested in the lone pairs around a particular central atom or atomic center. We're not really now interested. The lone pairs of chlorine in carbon tetrachloride, for example, are not that interesting. We're not worried about those electrons on the bonded atoms. Bonding electrons, again, everybody knows what we're talking about. This is the bond, and so bonds are very important in establishing molecular geometry. We have lone pairs that help establish bond angles and the arrangement of bonded atoms, but it's the bond pairs that really end up giving us our geometry, and you'll see how that works later. Electron repulsions, again, I think everybody remembers the law of electrostatics. Electrons repel one another, but again, the repulsions we're interested in VSEPR are those lone pairs or bond pairs around an atomic center, so around the central atom or atom of interest. And the geometry then refers to the shape of a molecule, and that's due to the orientation of bonded atoms around a central atom or atomic center. And again, bonded atoms, this is important. It's only the bonded atoms that gives rise to the geometry. The lone pairs are still there, but they do not come into the shape of it. And again, you'll see how that works later. So those are the definitions. If you want to pause the video now, it might be a good idea, and I'll wait for a minute. So molecular geometry, or the shape of the molecule, arises when a molecule maximizes electron nucleus forces and minimizes nuclear-nuclear repulsions and electron-electron repulsions. And VSEPR then is really concerned with these electron-electron repulsions. So how does the geometry come about? Well, there's two things we want to consider. First, it's about how many and the type of electron domain that is attached to a central atom, atomic center. So that's the first thing we can look at. And secondly, it's about the nature of those electron domains and how their arrangement brings about a shape. Now, if we look at this particular molecule here, we can see an example of an electron domain, which is in this case a bond. So that electron domain would be known as a bond pair. And so we have two electron domains around this central atom. The red atom is the central atom. So how many? Well, there's two electron domains. Well, actually, what you can't see is two more, and that's what we mean by the nature of those electron domains. So we have another type of electron domain here, and that's this yellow one, and that's a lone pair. And so that's what becomes important. This first one I showed you, we get the shape from that particular molecule. The geometry rises from this molecule that has three atoms in it. But the nature of that shape, how that shape ends up getting established, is due to the lone pairs that are on this molecule, attached to this molecule, and the bond pairs. So you'll see a lot of these types of diagrams in the coming videos, because it's really important that you be able to form that link between the nature of the electron domains, which is in this right-hand picture, and how that leads to an actual molecular geometry, and that's this left-hand picture. First of all, though, we have to talk about how these repulsions get established. And that's what I'm going to focus on for the rest of the video. So here's a simulated bond, or two bonds around a central atom. Obviously, it would not remain like this for reasons that will become clear in a minute if you're not sure yet. But what I want to just point out is we have a central atom. In this case, we have two bond pairs. So when you see bonded atoms, you know you're talking about the electron domain will be a bond pair. Okay, so and bond pairs often get shortened to BP. So we have a bond pair here. That's one bond pair, and this is a second bond pair. And so the bond pair is stretched or orientated along basically this axis between two bonded atoms. So the central atom and the bonded atom at the top here. So each one of those nuclei is pulling those electrons towards itself, so they kind of get spread out between the two bonds, or two atoms. And so the same is said for this lower or horizontal bond pair. It's spread out along an axis between two bonded atoms. And so when they spread out like that, we can look at this gap between them, or space between them. So this is known as an interpair distance. And as it says, this is a long interpair distance. And that's a relative term, but it is long because the electron domains, or the electrons, are being pulled away from the central atom in both cases. And when they're being pulled away in both cases, you're maximizing the distance between them. And so if you remember Coulomb's law, force proportional to 1 over d squared. So we have a long interpair distance. That means the distance is increased. And so the force, so if we increase distance, the force of repulsion in this case is going to decrease, inverse relationship. So this is the first type of repulsive force you see in atom or in molecules, and so it's called a bond pair force. And a bond pair force is the weakest. We're going to see three different ones, and the BP force is the weakest, and that's due to the relatively large distance between them. Okay, so again, it's a relative term. Obviously, in real terms, that distance is exceptionally small, but it is the largest of the three we're going to look at. So bond pair force of repulsion is weak between two bonded atoms. So the next force we want to talk about is this one, and that's, again, you can see that interpair distance is intermediate, so it's smaller. So again, we talk about a lone pair here. This is a lone pair. And we still have a bond pair, but that lone pair is there. Now, why is the distance smaller? Well, you can imagine the lone pair is there because we removed the bonded atom up here. So the bonded atom is gone, and therefore there's no nuclei from a bonded atom pulling the electrons away from the central atom. So the only thing pulling electrons is the central atom. So the electrons will be able to get closer to the central atom. We still have a bond pair here, and so that hasn't changed. That distance is, that orientation, that electron pair is about the same. But the distance is decreased because the lone pair is now closer to the nucleus. So for lone pair, bond pair repulsion, it's going to be larger than bond pair because the distance is decreased. So the distance between the electron domains is less, and that increases repulsion. So again, back to Coulomb's law. If we decrease the distance between those repulsive forces, or repulsive electrons, the force of repulsion will be larger. And the final one then, and again, you should be able to see this now, this interpair distance is virtually unrecognizable as actual distance. And so lone pair force or repulsion is the largest. So it's the largest repulsive force we see, and that's again due to smallest distance between the electron domains. And that's summarized on this next slide. Again, going from largest to smallest from left to right. So when there's no bonded atoms, two lone pairs only, interpair distance is small, force of repulsion is strong. If we add a bonded atom, we have an slight increase in the interpair distance due to the nature of a bond, and that force of repulsion will be less than the lone pair force. And then if we have two bonded atoms, the interpair distance is the largest, and the bond pair repulsion then is the weakest force of repulsion. And so we'll see next video all these, the nature of these repulsive forces is going to give rise to different molecular geometries. But that'll have to wait till the next video. And that concludes this video.